Hi, my name is Louie, and today I'll be talking about joint work with Ted on near-optimal de-randomization of medium width branching programs. So just for a brief outline of what the talk will look like, first I'll touch on some context and motivation for the problem. Then I'll detail some prior approaches, namely those of Savage and Sachs-Joe. And lastly, I'll touch on exactly what our contributions are and the approach we use to get them. Broadly speaking, this line of work is following in line with the conjecture of RL versus L, or can also be seen as work towards the BPL versus L conjecture. And this conjecture is interested in whether or not randomness is really essential for space-bounded computation. So it's broadly believed in the complexity theory community that, in fact, randomness is not necessary for space-bounded computation. So a conjecture that is widely believed is that for any randomized algorithm solving a decision problem on inputs of size n using space only order log n, there would also exist a corresponding deterministic algorithm that decides the same language using space also order log n. So this deterministic algorithm would seem to be some kind of de-randomization of the randomized algorithm. And the question that's kind of at the forefront is whether or not we can actually prove that these deterministic algorithms exist. So the work we'll be talking about today is essentially working towards hopefully eventually proving this conjecture. It turns out that one very useful tool in this field, or one very useful model in this field, is the model of ordered branching programs. So the kind of the way to imagine these branching programs is that you have some randomized algorithm A, which takes an input X, as well as a random tape or a set of random bits R. And what we do is that we create a graph, which has a bunch of different layers. In layer I of this graph, all of the nodes correspond to the possible memory configurations of the algorithm. So if our algorithm was given some kind of S bits of working space, this would lead to an ordered branching program where every single layer has 2 to the order S nodes. So in a sense, there's kind of a bijection between all the possible memory configurations in the Turing machine and all the nodes in each layer of the graph. The way that the transitions work in this ordered branching program is that we read off some random bit between the ith and I plus first layer of the graph. And depending on what this random bit is, this corresponds to a transition between possible memory configurations in the Turing machine. The reason this makes sense is that if we have a randomized algorithm, once our input X is fixed, the only kind of deviations in the memory configurations of the Turing machine correspond to the random bits that are being read by this algorithm. So this leads to a kind of perspective of randomized algorithm as taking in random bits, and correspondingly you have a graph where the memory configurations are changing after each corresponding bit that's been read. In this talk, we'll be referring to something called the polynomial width regime. And this means when you have inputs of size n, we're using n random coins, and correspondingly, the Turing machine is allowed space order log n, which corresponds to a branching program that has 2 to the order log n nodes in each layer, which is again going to be polynomial in n number of nodes in each layer of the ordered branching program. To see how these ordered branching programs are evaluated, we can start with a pretty basic example here. We can imagine that we're starting our evaluation at some vertex v naught, and in order to determine which node we're going to transition to in the second layer, we'll read the first random bit. If we say that this first random bit is a 0, we transition according to this blue line and end up at this bottom vertex in the second layer. We'll then read the second random bit. If this turns out to be a 1, we transition according to the red line. And then finally, we'll read the third random bit. If this also turns out to be a 1, then we'll transition to this final vertex, VA. And now, depending on whether or not this final vertex is an accept vertex or a reject vertex, we'd correspondingly say that the algorithm is outputting a 0 or a 1. So it turns out that viewing these ordered branching programs as a model for randomized computation is very valuable because it also implies a sort of complete problem for the case of these small space randomized algorithms. And the way we can view these is that, say, between this first layer and the second layer, we're essentially doing a probabilistic transition from being at some vertex I to some vertex j in the second layer. And correspondingly, the way to think about this transition is that with, say, a probability 1/2, we're going to read a random bit that's a 0, and we transition according to these blue edges. With probability 1/2, we read a 1 and transition according to these orange edges. We can actually write this probabilistic transition as a matrix, and then to kind of see what the distribution of vertices in the second layer is, it would correspond to just multiplying by this transition matrix. If we multiply together all the matrices from this first transition, the second transition, all the way up to the nth transition, this will give us a model of what the distribution of the final states of the Turing machine will be after reading off n random bits. So this is why this problem of iterated matrix multiplication is kind of the complete problem when we're talking about decision algorithms in small space. And I guess stated, the problem is exactly given n stochastic matrices m1 to mn, which are W by W matrices, where W is again the width of these branching programs we talked about before. We want to estimate the product m1 times m2 all the way up to mn, up to some kind of additive error, which will be 1 over polynomial in n. So there's been several algorithms for this problem. First, we have Savage, who, I guess by a simple modification to his algorithm for a non-deterministic space, you can show an algorithm that solves this approximated iterated matrix multiplication in space log n times log w. A little bit more non-trivially, Sachs and Joe in 1995 demonstrated an algorithm which gets order square root log n times log n plus log w. And then more recently in 2022, Cohen, Duran, Sperlow, and Tashma gave an algorithm which gets space order square root log n times square root log n times log w up to some additional log factors, specifically for the case where m1 equals m2 all the way up to mn. These are all identical. So the contribution in our work today will be to show that you can actually drop this final condition of all the matrices having to be equal and still get exactly the same space complexity. So kind of restated, our result today is given n stochastic matrices m1 to mn, estimate the product m1, m2 all the way up to mn. Exists a deterministic algorithm for this problem that runs in space O tilde square root log n times log w plus log n. And I should mention in the same conference, Cohen, Duran, Sperlow, and Tashma have this exact same result with a different proof. And I'd encourage you to watch their video as they might touch on some of the details that we skip over. And then I should say they will touch on some of the details that I will skip over. So just to see exactly what these parameters that we've just discussed look like, in this orange line, we've plotted Sachs-Joe. So this is getting exactly this log to the 3/2 n space, kind of regardless of the width w is, as long as the width w is sufficiently small, as is plotted in this image. Savage has gotten exactly this log n times log w is plotted in this blue line. And for us, plotted in this green line, is our square root log n times square root log n plus log w. One way to kind of view our contribution is that specifically in the case where w equals 2 to the square root log n, we actually get near optimal derandomization in the sense that we still have a space. The space is approximately O tilde log n, which is why the title of our paper is Near Optimal Derandomization of Medium Width Branching Programs. Specifically, medium width is what we're calling this regime where w equals 2 to the square root log n. The improvement that we have over Sachs-Joe kind of deteriorates as w approaches n. And in fact, when w equals n, we recover exactly the result of Sachs-Joe up to some extra log factors. Now for some brief overview of some prior work. First, I'll briefly touch on Savage. So again, our problem is to compute this approximated iterated matrix multiplication, m1 all the way up to mn. And for now, we'll just concentrate on calculating the ijth entry. So if we let L denote the first n/2 matrices in this product, and R denote the last n/2 matrices in this product, if we assume that we have some kind of oracle access to L and R, then we'd be able to compute the ijth entry in the complete product of L times R using approximately only order log W extra space. And this is just by computing the sum from k equals 1 all the way up to W of Lik times Rkj. Because k only goes up to W, where W is the width of the matrix, just keeping control of this counter would be space order log W, and then actually keeping track of the entries would be maybe another order log W space. Now, because we've kind of split the problem in two, you can imagine this is giving birth to an entire tree of depth log n. And we're saying at each node, given access to all the information below it, the space to kind of combine all the results is order log w. So kind of by these theorems for composing space-bounded computation, the total space that will be taken by composing this algorithm at every step would be order log n times log w. And just stated another way, at every level of the tree, we're using space log w, and there's log n levels to this tree because we have like a division factor of 2 in each node. So in total, this is again space order log n times log w. So Sachs and Joe tried to improve this by saying, what if we can actually make a bigger branching factor? So now instead of saying, okay, we'll split it into 2 separate matrices, they say, let's split this into 2 to the square root log n different matrices at each level of the tree. Now, this means that instead of the depth of the tree being order log n, the depth of the tree will simply be square root log n. So if we can choose some kind of parameters to do a clever, iterated matrix multiplication at each level that takes space order log w plus log n space, then this would lead to a total space consumption of order square root log n times log n plus log w. And when we're talking about Sachs-Joe for now, just going forward, I might only focus on the case where all of the matrices M are identical, because it turns out in the Sachs-Joe case, by some simple reductions, it suffices to analyze when all the M's are the same, just because they're not too concerned with specifically how this parameter W is performing. So for Sachs and Joe, when they set W equals to n, this total space consumption of the algorithm is square root log n times log n, which is just log to the 3/2 n. And this led to the landmark result that RL is contained in L to the 3/2, and additionally that BPL is contained in L to the 3/2. Recently, some work by Hosa actually improved this to L to the 3/2 minus little of 1, but this is a little bit disjoint from our work today. So a key tool that Sachs and Joe used, and it's also used in the algorithm we'll present today, is the Nissan pseudorandom generator. Broadly speaking, Nissan pseudorandom generators is saying that there exists some pseudorandom generator, which I haven't really defined exactly what that is yet, but it takes an offline seed H, which has length order log n times log n w over epsilon. And with high probability over H, we kind of get a pseudorandom generator that now takes an online seed of length order log n w over epsilon and maps it to an n-bit string, such that now this n-bit string produces walks that fool these read-once branching programs of length w, or of length n and width w up to error epsilon. So again, there's 2 things to keep track of here. We have an offline seed, which is very long, which is it's log n times log n w over epsilon. And then we have a kind of shorter online seed, which is going to be of length order log nw over epsilon. And what we want is kind of, I guess the way Nissan works is that over a random choice of H, it turns out that most choices of this online seed will be good. So what Sachs and Joe wanted to do, I guess a simplified version of their algorithm, is to say, choose some parameter m, which will be 2 to the square root log n. Let w be the w, the same width of this branching program, and let epsilon be 1 over n squared. These are the parameters for the Nissan pseudorandom generator. And now they're going to store an offline seed H of length order square root log n times square root log n plus log w over epsilon. Now, we're going to define some sequence of matrices called w sub I, and we'll let w1 just equal this matrix M that we want to power to get the nth power of. Now for square root log n iterations, we let w sub I plus 1 equal Nissan of wi. And again, this is approximately just wi to the 2 to the square root log nth power. Now, as stated, this algorithm doesn't work. And there's a kind of subtle reason for this. So if you remember in the definition of Nissan's pseudorandom generator, we said that with high probability over a random choice of H, the seed's output of Nissan's generator will be good for like an arbitrary graph. The problem is that then this is kind of enforcing that the seed that you've chosen is independent of the graph G that we're operating on. But in the way we've set up the problem right now, W2 equals Nissan sub H of W1. So this means that W2 actually depends on H and our choice of H is no longer independent of this matrix W2, so it doesn't really make sense to argue that the same seed H that we use for W1 will also work for W2. And it was this observation that Sachs and Joe really had to try to fight to overcome, and led to their a kind of motif of shifting and truncating, which has also been used in many subsequent works. In a couple of words, what they do is at level I, they inject some noise into the resulting operation. That is, they kind of entry-wise add a random number, which is order 1 over poly NW. And it turns out that when you round the result of adding this element-wise noise to the result of calling Nissan on Wi, this actually turns out to equal, like exactly equal with high probability, the result of rounding the same noise added to the true powering of Wi. And because of this equality, it turns out that Wi plus 1 is now defined without reference to Nissan sub H. So you can reuse this offline seed H, and it'll still be good with high probability. However, there's one key limitation of this shifting and truncating method in our context. It turns out that if you have n distinct matrices, in order to have the randomness be good enough for you, you need to invest at least order log n random bits in that level. So this will even hold when the dimension of each matrix is very small, like that is when W is much smaller than n. So even for these long, narrow directed graphs, you would still need to invest log n bits per level. Because you have square root log n levels, this leads to a log to the 3/2 n space, even if W is very small. To overcome this issue, kind of Cohen, Deron, and Sperlow, in the case where all the mi's are equal, you can actually get rid of or the shifting and rounding is still okay because you don't have n distinct matrices. If all the mi's are equal, you just have one matrix. So they show that when all the mi's are the same, then you can do rounding with fewer random bits. And to deal with some kind of error blowup, you can just add Richardson iteration and get an algorithm that works for just as when all the mi's are equal. So using their same error reduction technique, if we can get rid of the shifting and rounding for distinct matrices, then we'll get an improvement to the space bound overall. So our solution is to do exactly this. We show that the shifting and truncating operation can be eliminated entirely, and the algorithm will still succeed with high probability as long as we're using the same error reduction technique of Cohen, Deron, Sperlow, and Tashma. So to understand how exactly we do this, we take a peek inside what Nissan is actually doing. So Nissan is producing walks, but somehow we want to use it to approximate like powers of matrices, or multiple applications of different matrices. So the question is how we can go from applying a matrix M to actually looking at a graph that we're taking walks on. So Sachs and Joe tackle this issue by defining something called a canonicalizer, which takes some kind of stochastic matrix M, maps it to a set of vertices and edges. The way this works is that if this stochastic matrix is W by W, it's kind of defined on a ground set of W vertices as a transition. So you can create a 2-layer graph where you try to embed these probabilities as the transition probabilities in the graph. So as an example, if we had the first row of M1 having values 0.2, 0.3, and 0.5, what you want to do is have an approximately 0.2 probability of transitioning from vertex 1 in layer 1 to vertex 1 in layer 2, 0.3 probability going from 1 to 2, and then 0.5 probability of going from 1 to 3. So how we actually do this when it's in the discrete setting, because we can't exactly enforce these transition probabilities, is we just make some large alphabet, and then we can kind of discretize and round so that we get approximately the first M11 times D edges going from state 1 to 1, approximately M1 times 2, M1 comma 2 times D edges going from 1 to 2, and then similarly M13 times D edges going from state 1 to state 3. So using this canonicalizer, what we show is that for some stochastic matrix M, there exists some special error graph E that we'll define later, such that walks that fool GM and also fool E will also fool G of M prime for any M prime that's close enough in some matrix norm to M. So what this means in our setting is if Nissan sub H, which generates some walks, if these walks are good for GM and for E, then it is good for GM prime, even for M prime that depends on H. So to actually see exactly what this E is and how we can derive a statement of this form, we're going to take a dive into actually analyzing adaptive Nissan. So let's actually see what the difference is here. Prior work has said, GM and GM prime have, like the similar walk, the walk matrices are very similar. We need something that's a little bit stronger than that, because just these matrices being similar does not suffice to argue that Nissan performs well. So now we can take a different look at exactly how this canonicalization procedure is working. So we can kind of open up exactly what we were doing before, where we had capital D, like the size of our alphabet was capital D. So we can write this as each vertex has capital D edges coming out of it. And now we can color these edges corresponding to which vertex they're transitioning to. So in our previous example, what we'd want to do is say there's 3 vertices or something. This means that from vertex 1, the first M11 times D of these edges would be colored as blue, meaning they go from vertex 1 on layer 1 to vertex 1 in layer 2. Correspondingly, the next M12 times D edges we would color red, saying they going from vertex 1 to vertex 2, and then the remaining edges we'd color green, transitioning to some other vertex. We could do the same canonicalization procedure over the same size alphabet for G of M prime. Here, almost all the edges will be the same color. For like the same edge label, they'll almost all be the same color. But because the matrix norms aren't exactly the same, there can exist some edge labels such that the coloring of the edges are slightly different. Now on the left, we'll designate some vertices as being boundary vertices, and these are exactly where we're changing colors, either going from blue to red or red to green. And we'll kind of look at some window around the edge labels corresponding to boundary edges on the left, and we'll call these a bigger set of boundary edges on G of M prime. And the key insight that we want to use here is that we're going to choose a window for these boundary edges on the right that is sufficiently big such that they capture all the possible edge labels where the colors are disagreeing between G of M and G of M prime. And if we choose this set of boundary edges to be sufficiently large, then we're guaranteed that if a walk never traverses a boundary edge, then it will always be the same color, because all the remaining edges will have colors that are exactly the same between the canonicalization of M and the canonicalization of M prime. So it turns out that we can actually build an indicator branching program, which is exactly 1 if you ever take a boundary edge, and is 0 if you never take a boundary edge. And because this is still a read-once branching program, and because these boundary edges are only defined in terms of the boundary vertices, which are defined in terms of M, this is again a read-once branching program which has no dependence on the offline seed H, which means that walks generated by Nissan sub H will still be good, and will never take too many boundary edges because they still fool this class of branching programs. Finally, we have one final observation, which is because the matrix norms are sufficiently close, it turns out we can actually bound the size of each of these sets of boundary edges on the right. Each one of these will capture approximately an epsilon fraction of the edges. So because there's W vertices, this means in total the number of edges that's captured is at most kind of an epsilon W fraction. Finally, putting this all together, if the matrix norms are if the matrices are sufficiently close in some matrix norm distance, every row sum will differ by at most epsilon. So denoting the boundary as these kind of edges closest to the thresholds, which is again defined only in terms of M and epsilon. It turns out that as long as a walk from Nissan sub H never traverses a boundary edge, it'll behave the same on G of M and G of M prime. And we have this kind of fact that the probability that you hit a boundary edge is sufficiently small. So all that we get from evaluating on G of M versus G of M prime, we get some error calculation, which is at most an epsilon W factor. So our error has blown up in 1 step from epsilon to epsilon W, which means that we can't simply just reapply Nissan a bunch of times on itself. But instead, we can actually use an approach from Cohen, Duran, and Sperlow, where we use Richardson iteration to repair this loss at each level. We use log W levels of Richardson iteration for a total space requirement of log N, log W. There's some other tricks that we have to use as well, and we encourage you to read the full version of the paper to see all of these. But in like the final algorithm, the way it works is we take an offline seed H of length ordered log N plus square root log M log W. We set this W1 to equal M. And now for I equals 1 to square root log N, we let W sub I plus 1 equal Nissan sub H of Wi, which is now approximately the 2 to the square root log nth power. We use Richardson iteration to bring the error back down. Now the matrix norm, the matrix norm of the difference between the true power and the power that we have is sufficiently small, such that we can use our canonicalization argument to argue that when we reapply Nissan, the error actually doesn't blow up too much, and we can bring it back down and kind of repeat this process, which ultimately results in a good approximation to the product. And here we've never actually used any facts about the matrices being the same, so this will work for distinct matrices. Lastly, just want to mention that there's concurrent work at this conference by Cohen, Duran, Sperlo, and Tashma, which you should check out. And then thank you.